A giant squid the length of a school bus is fighting something in the dark, a mile below the ocean's surface. The pressure down there would crush a car like a tin can, and the thing it is fighting moves slower than you walk, has been alive for 200 years and cannot see clearly. Yet somehow, the shark is winning. We're going to find out how. We will go into the pressure zones, track the scars, and follow the science that prove these battles are real. If you enjoy what we build together here, subscribe and hit like. Now brace yourself. We begin. For most of human history, the giant squid was a ghost. Sailors told stories about it for centuries. Ancient Norse sailors called it the Kraken. They described a creature so massive it could pull a ship underwater. Explorers drew it on maps as a warning. Every serious scientist in the 18 and 1900s dismissed it as legend, as fantasy, as the kind of story tired sailors tell after too much rum. Then the bodies started washing up. Dead giant squids began appearing on beaches in the 1800s, mostly in Newfoundland and New Zealand. They were enormous. The longest one measured nearly 43 feet from the tip of its body to the end of its longest arm, about the same length as a city transit bus. Scientists measured the eyes. They were the size of dinner plates. The suckers on the arms were ringed with sharp, curved teeth, made of a material harder than human fingernails. This animal was absolutely real, but real and visible are two different things. Nobody had ever seen one alive in its natural environment. Every specimen scientists studied came from a beach, a fishing net, or the stomach of another animal. That last source, the stomach, is where everything changed. In the mid-1900s, marine biologists started doing something that sounds simple, but turned out to be revolutionary. They began cutting open dead sperm whales and cataloguing every single thing they found inside. Sperm whales dive deep, over a mile down, and they eat. Whatever they eat leaves evidence, and what scientists kept finding over and over were giant squid beaks. A squid beak is almost indestructible. The rest of the squid is soft tissue gone within days, but the beak survives. It is hard, curved, shaped almost like a parrot's beak but jet black, and it can sit in a whale's stomach for months without breaking down. Scientists counted them. Some whales carried dozens. One whale had over 18,000 beaks inside it. That single discovery proved the giant squid existed in enormous numbers, spread across almost every ocean on Earth. So scientists knew the squid existed. They knew it lived deep, and they knew something else was eating it. The sperm whale connection got the headlines, but a quieter discovery was happening in university labs and on research vessels across the North Atlantic. Scientists were examining sleeper sharks, a group of large, slow, deep-water sharks found in the Arctic and North Pacific, and they were finding the same thing inside them. Squid beaks. Giant squid beaks. Dozens of them, packed into stomachs of sharks that barely moved fast enough to chase a sea turtle. That was the puzzle. A shark that's slow should not be catching something that big. The question sat in scientific literature for decades, tucked into footnotes and species reports, mostly ignored. Everyone assumed the sharks were scavenging dead squids off the seafloor. Clean answer, simple answer. Simple. But a team studying sleeper shark behavior in the North Pacific started finding something that made the scavenger explanation fall apart. The sharks had scars, fresh ones, deep ones, arranged in patterns that matched exactly the sucker rings of a giant squid arm pressed hard against flesh. Those scars meant one thing: the squid had been alive when the shark caught it, and the squid had fought back. What happens in that darkness, a mile below the surface, turns out to be one of the most violent and least understood conflicts in the animal kingdom, and it gets stranger from here. Picture the laziest animal you've ever seen. A dog sleeping in the sun. A cat that hasn't moved from the couch in 6 hours. Now imagine that animal is 30 feet long, weighs over a ton, lives in water so cold it would stop your heart in minutes, and has been alive since before your grandparents were born. That is a sleeper shark. The name fits. These animals move at an average speed of about 1 mile per hour. A brisk human walk is 4 times faster. A sea turtle cruises faster. Even some species of jellyfish drift faster than a sleeper shark chooses to swim. Scientists first assumed this slowness made them weak, passive, minor players in the deep-sea ecosystem. That assumption was completely wrong. There are several species grouped under the sleeper shark label, but the one most connected to giant squids is the Pacific sleeper shark. It grows up to 23 feet long, roughly the length of a moving truck. It lives in the North Pacific from Japan to Alaska, diving to depths of over 6,000 feet. That is more than a mile straight down, into darkness and pressure that most ocean life cannot survive. Down there, the water temperature hovers just above freezing. A human in that water without protection would lose the ability to move within minutes and die within the hour. The sleeper shark thrives in it. Its body runs at the same temperature as the surrounding water, which means it burns almost no energy keeping itself warm. Every calorie it consumes goes towards staying alive and growing. That is part of why these animals live so long, which we will get to shortly, and part of why they can survive on very little food. The eyes of a sleeper shark carry a secret that sounds more like a curse. Many sleeper sharks have parasites living directly on their corneas, small crustaceans called copepods that attach to the surface of the eye and feed there permanently. The damage leaves the shark partially or even nearly blind. For years, scientists thought this made sleeper sharks helpless. Blind, slow, living in total darkness. How could they possibly hunt? The answer lies in what they can sense beyond sight. Sharks in general possess a system of organs called the lateral line, which detects pressure changes and vibrations moving through the water. They also have sensory pores concentrated around the snout that pick up the electrical fields produced by every living animal's muscles and heartbeat. In total darkness and near zero visibility, a sleeper shark can feel a giant squid moving from dozens of feet away. It feels the water shift. It feels the electrical pulse of beating hearts. Slow does not mean unaware. Scientists studying these animals with underwater cameras were repeatedly surprised by what they saw. A sleeper shark approaching prey does not rush. It glides, barely moving its tail, covering ground in total silence, closing the gap so gradually that prey animals sometimes don't react until the shark is already within striking range. And here is the part that keeps researchers talking. The sleeper shark's jaw can open with almost no warning movement. Most sharks telegraph a bite by lifting their snout and dropping their jaw visibly. The sleeper shark can strike with a motion so small and fast that high-speed cameras almost miss it. That combination, stealth, electrical sense, explosive bite, turns a slow shark into something far more dangerous than it looks. And what it's hunting in those depths is a living weapon with 45 feet of armed arms. That matchup deserves a much closer look. The discovery happened by accident, the way most important scientific finds do. In the 1980s, a team of marine researchers working in the Bering Sea was collecting sleeper sharks for a population study. The work was unglamorous, measuring bodies, tagging animals, logging data, standard field biology. When a large Pacific sleeper shark was brought aboard for examination, one of the researchers decided to check the stomach contents, a routine step for understanding what sharks in a given area were eating. What came out of that stomach stopped the team. Packed inside, along with the expected fish remains and some squid tentacle fragments, were 3 giant squid beaks. Each one was the size of a large man's fist, jet black, perfectly intact. The surrounding tissue was already partly digested, but the beaks sat there unchanged, because squid beaks are made of a protein structure so dense that stomach acid barely touches them. 3 beaks meant at least 3 giant squids in one shark. The team flagged it in their report but didn't publicise it widely. Giant squid were still rare enough, and sleeper sharks understudied enough, that the find felt like an anomaly. A strange footnote. Maybe the shark had scavenged 3 dead squids off the sea floor. Nobody pushed hard on the question. Then other researchers started finding the same thing. Over the following decade, stomach content studies from sleeper sharks, caught across the North Pacific and Arctic, turned up giant squid beaks repeatedly. Some stomachs held one beak, some held several. The sheer frequency of the finds across different locations made the scavenging explanation harder to accept. Dead giant squids don't float to the seafloor in large numbers. They are soft animals. When they die at depth, they decompose fast. For a sleeper shark to consistently find and eat intact giant squids, something more active had to be happening. A marine biologist named Tracy Sutton, working years later on deep-sea food web studies, described the problem clearly. The stomach evidence pointed toward predation, meaning active hunting, but nobody could figure out how a shark that slow caught a squid that fast. The beak evidence alone changed the scientific picture of the sleeper shark from minor scavenger to something worth taking seriously. Before these findings, most deep-sea ecology research treated sleeper sharks as background animals, present but unimportant. The beak discoveries reframed them as potential apex predators, operating at depths humans had barely explored. And the deeper researchers dug, the stranger it got. Scientists began cross-referencing the stomach data with something else: the body condition of the sharks themselves. Sleeper sharks carrying giant squid beaks tended to be in excellent physical shape, well-fed, healthy fat reserves for animals that live in near-freezing water. If they were scavenging randomly, you would expect more inconsistency. The consistent health profile suggested a reliable food source, something they could find and exploit on a regular basis. The final piece that convinced most researchers came from tissue analysis. When scientists examined the stomach lining of sharks that had recently consumed giant squids, they found something the scavenging theory couldn't explain: fresh injury marks on the stomach wall itself, punctures, cuts, evidence that something with hard, sharp structures had been actively moving inside the stomach, resisting digestion. A dead squid does not fight back from inside a stomach. A live one does. That detail landed in a published paper in the early 2000s and quietly rewrote the conversation. The question shifted from whether sleeper sharks ate giant squids to how, exactly, they caught them. And the answer required going somewhere humans had never managed to look in real time. Stand at the edge of a 5-story building and look down. That distance from the roof to the sidewalk is roughly how long a fully grown giant squid can get from the tip of its 2 longest arms to the back of its body. 45 feet, the length of a school bus with room left over. Now imagine every inch of it is built for attack. The giant squid's body has 2 distinct sections. The mantle is the main tube-shaped torso where all the vital organs are packed. In a large adult, the mantle alone can reach 6 feet long. Behind the mantle, 8 thick arms extend forward, each one lined with suckers from base to tip. 2 of those arms are longer and thinner, called tentacles, and they are the main striking weapons. A giant squid can launch those tentacles outward at remarkable speed to snag prey several feet away. The suckers are where the design gets brutal. Each sucker on a giant squid's arm is ringed with a circle of hard, curved teeth. These are called sucker rings, and under a microscope they look like tiny serrated blades arranged in a tight circle. When a sucker clamps onto something, those teeth bite in. The more the prey struggles, the deeper the teeth dig. Scientists who have examined sucker ring wounds on whale skin and shark skin describe them as looking like branded rings, permanent circular scars burned into the flesh. A squid with 8 arms plus 2 tentacles, each covered in dozens of these sucker rings, can apply hundreds of individual biting grip points simultaneously. Against a shark's tough hide, those rings leave marks that last for years. The eyes are the detail that most people find hardest to believe when they first hear it. A giant squid's eye can measure up to 10 inches across. That is about the same diameter as a standard dinner plate, and it is the largest eye of any animal on Earth. The size is a direct adaptation to deep water darkness. Down below 3,000 feet, the only light comes from bioluminescent animals, faint biological glow scattered and dim. An eye 10 inches wide can gather vastly more of that faint light than a small eye, giving the squid a meaningful visual advantage in near-total darkness. But here is something researchers discovered that flipped the obvious assumption. Despite those enormous eyes, giant squids may be effectively colorblind. They see the world in shades without true color differentiation, at least based on the structure of their retina. Scientists suspect this is compensated by their extraordinary sensitivity to contrast and movement. The squid doesn't need to see color to detect a large, slow shape drifting toward it in the dark. The beak sits at the center where all the arms meet, pointing forward. Made of chitin, the same material in insect shells, it is the hardest structure in the squid's body. Strong enough to bite through fish bone, strong enough to puncture thick, rubbery shark skin, and as the stomach evidence already told us, strong enough to survive inside a shark's stomach long after everything else has dissolved. The giant squid's body is essentially a 45-foot weapon system. Every part of it evolved to catch, grip, bite, and not let go. What it faces in those deep trenches is a predator that has spent hundreds of years learning exactly how to get past all of it. Take a can of soda, hold it in your hand, feel how solid it is. Now imagine a force pressing on every surface of that can from every direction at once. A pressure 300 times stronger than what you feel right now at the surface. That can would be crushed flat in a fraction of a second. At 3,000 feet below the ocean's surface, that is the pressure on everything that lives there. The battles between giant squids and sleeper sharks happen in this zone, and in many cases much deeper. Scientists tracking sleeper sharks with depth recording tags have logged dives past 6,000 feet. Giant squids have been found at similar depths, and some evidence suggests they can go even deeper. The zone where these two animals most frequently overlap sits between roughly 3,000 and 6,000 feet down, a region called the bathypelagic zone by scientists, though most people simply call it the midnight zone. Down here, sunlight is completely gone. Every photon of solar energy is absorbed by the water column long before it reaches this depth. The only light that exists comes from living things producing it themselves. There is no current from the surface. The temperature stays just above 32 degrees Fahrenheit year-round. The pressure is measured in hundreds of atmospheres. Humans have visited this zone only in specially armoured submersibles with hulls several inches thick. Even those vehicles operate under extreme risk. A single structural failure at that depth means instant total compression. The vehicle and everyone inside would be destroyed faster than any conscious experience could register it. So how do giant squids and sleeper sharks survive there? The squid's body is almost entirely made of soft tissue filled with a fluid that contains ammonium chloride, a chemical compound lighter than seawater. This fluid permeates the squid's muscle tissue and makes the whole body essentially pressure neutral. The pressure outside matches the pressure inside, so the squid is never being crushed. It floats in chemical equilibrium with its environment. A squid brought to the surface dies partly because that equilibrium collapses when external pressure drops. The sleeper shark's solution is different. Its body tissues contain high levels of trimethylamine oxide, a compound that stabilizes proteins under pressure. Without it, the pressure at those depths would physically deform the proteins that make up the shark's muscles, enzymes, and cellular structures. The compound acts like a pressure shield at the molecular level, keeping the shark's biology functioning normally in conditions that would destroy a surface animal. Both animals evolved these solutions independently, arriving at different chemical answers to the same crushing problem. What makes this zone the setting for their conflict is a convergence of food and opportunity. The midnight zone sits directly below a massive layer of sea life that migrates vertically every day, rising toward the surface at night and sinking back down at dawn. Giant squids follow this migration, hunting in the layer above before descending. Sleeper sharks patrol the lower boundary, waiting. The overlap zone is where prey concentrates and where predators close in. In that darkness, At pressures that would kill most life on Earth, two giants find each other. And what happens between them when they do is something no human has ever seen from start to finish. What we know comes entirely from the wreckage left behind. That wreckage tells a story that gets more violent the closer you look. For most of the 20th century, the giant squid was studied exclusively through corpses. Every specimen scientists worked with was dead before they got to it. Dead on beaches, dead in nets, dead in stomachs. The animal was undeniably real, but its actual behaviour, how it moved, how it hunted, how it reacted to the world around it, was completely unknown. Scientists were essentially trying to understand a living creature using only its remains. Sending cameras deep enough to find one alive presented a problem that took decades of technology development to solve. The ocean at 3,000 feet is dark, cold, and crushingly pressurized. Early underwater cameras couldn't handle that depth. The housings failed. The lights attracted the wrong animals or scared away the right ones. Research vessels could lower equipment that far, but keeping it stable and positioned in the right location, with no guaranteed target in sight, cost hundreds of thousands of dollars per day. The first breakthrough came in 2004. A Japanese research team, led by marine biologist Tsunemi Kubodera, rigged a camera system with bait suspended at a depth of around 3,000 feet off the Ogasawara Islands in the Pacific. They left it running for hours at a time across many dives. On their 83rd attempt, something triggered the bait. A giant squid attacked the camera rig. The footage, roughly 500 frames captured over several seconds, showed the squid coming in fast from below, wrapping two tentacles around the bait and then pulling. The tentacle that wrapped around the hook tore free as the squid tried to escape. The remaining piece of tentacle was recovered from the camera rig and measured 18 feet on its own. That number tells you how large the whole animal was. The footage answered one burning question immediately. Giant squids were active hunters. The approach in that video was deliberate and fast. The animal moved with precision. A scavenger drifting on currents doesn't launch a vertical attack on a suspended target. This squid came in with intent, but the footage also raised a problem that researchers still wrestle with. The squid in that video was attracted by bait and by artificial light. It was interacting with human equipment, not behaving naturally. Scientists got their first glimpse of a live giant squid, but they were watching it in a situation it would never encounter in the wild. Its actual hunting behaviour, in total darkness against natural prey, remained unseen. 2012 brought the next milestone. A team using a specially designed low-light near-infrared camera system managed to film a giant squid in the wild at depth near the same island chain, without bait, without bright lights. The footage lasted only a few minutes before the squid descended out of range. What it showed was an animal far more graceful than anyone expected. The squid moved by pulsing water through its mantle in controlled jets. It changed direction instantly. At full speed, it covered ground in bursts that no camera operator could predict or track. That speed, in an animal 45 feet long, was sobering for anyone who had assumed the giant squid was a slow, lumbering target. The sleeper shark, by contrast, had been filmed dozens of times, and its movements were well documented. Watching the two pieces of footage side by side, researchers faced a new and pressing question. How does the shark get close enough to a squid that fast to make a kill? The answer involves something the shark does that the squid never sees coming. A marine biologist examining a sleeper shark can read its history on its skin. The scars are unmistakable once you know what to look for. They appear in rings, circular marks roughly 1 to 3 inches across, sometimes clustered in dense groups, sometimes scattered in lines across the shark's flanks, face, and around the mouth. Under examination, each ring shows the same pattern: a raised outer edge, a depressed centre, and in many cases small radial cuts around the circumference matching the tooth spacing of giant squid sucker rings. These are not bites or slashes, they are grip marks. The signature of sucker rings pressed hard enough into shark skin to leave permanent damage. Scientists began documenting these scars systematically in the early 2000s after the significance of the stomach beak evidence became clear. Photographs and measurements from dozens of sleeper sharks were compiled, and the data produced something useful: a map of where squids make contact during a fight, and from those locations, an outline of how the fights unfold. The scars cluster most heavily around the shark's head and upper body. This tells researchers that the squid leads with its arms toward the shark's front end, wrapping or pressing against the head and gill region. There are also significant scar concentrations around the shark's mouth and lower jaw. Scientists interpret this as evidence that squids attempt to block or grip the shark's jaw during an attack, a defensive response aimed at preventing the bite. Some sharks carry scars from multiple separate encounters. A shark with fresh raised scars alongside older faded ones has fought squids more than once and survived both times. Researchers have found individual sleeper sharks with over 40 distinct sucker ring scar sites across their bodies. 40 contacts, 40 moments where a giant squid's armed suckers dug into that animal's flesh. The shark survived all 40. That survival rate matters scientifically. It suggests the sleeper shark has developed or evolved some physical resistance to the squid's grip. A shark's skin, called dermal denticles, is made of tiny tooth-like scales pointing backward along the body. This structure is extraordinarily tough. Running your hand backward along a shark's skin draws blood. Forward, it feels smooth. That structure may be the shark's passive defense. Sucker rings can grip the surface but have difficulty penetrating the thick denticle layer deeply enough to cause serious injury. Researchers also noticed that the scars on sharks rarely appear below the mid-body. The tail region, the shark's propulsion system, is almost scar-free. If squids were wrapping around sharks randomly, you would expect scars everywhere. The concentrated front body pattern suggests the squid focuses on the head end, toward the shark's sensory organs and jaw, while the shark maneuvered its rear section out of the range. This detail revealed something nobody had considered before. Both animals were making tactical decisions during these fights. The squid wasn't just flailing. The shark wasn't just biting blindly. The scar evidence pointed to something closer to a structured confrontation. Two intelligent predators using specific strategies against each other in complete darkness. And that picture only deepened when researchers turned from the shark's skin to the shark's hunting behavior itself. Because how a nearly blind 1 mile/hour predator closes the distance on a 45-foot escape artist involves a method so unexpected it changed how scientists think about deep water predators entirely. A cheetah hunts with speed. An eagle hunts with vision. A sleeper shark hunts with patience so complete it barely looks like hunting at all. Understanding the sleeper shark's method requires forgetting everything you associate with shark attacks. No circling, no sudden charge from a distance. The sleeper shark's strategy is built around one principle: get close before the target knows you exist. Scientists fitted sleeper sharks with accelerometer tags, instruments that record every movement the animal makes, and the data revealed a hunting profile unlike any other large predator studied. Sleeper sharks spend the vast majority of their time moving at their characteristic crawl, barely 1 mile/hour, which produces almost no pressure waves in the surrounding water. A moving animal creates a bow wave in the water in front of it and turbulence behind it, and prey animals' lateral line systems are tuned to detect exactly these disturbances. The sleeper shark's near motionless glide produces so little disturbance that it effectively vanishes from the lateral line detection of nearby animals. It approaches like a ghost. Research published in the journal Deep Sea Research analysed the movement patterns of Pacific sleeper sharks near areas where giant squids were known to be active. The shark showed a consistent behavioural pattern: long periods of nearly stationary drifting, punctuated by short bursts of directed movement toward a specific point, followed by an acceleration spike lasting only 2 to 4 seconds. Those 2 to 4 seconds represent the strike. Everything before is the setup. The genius of this method against a giant squid specifically is timing. Giant squids are jet-propelled, capable of explosive bursts that cover significant distance in under a second. But that escape mechanism requires the squid to detect a threat first. A squid detecting a threat at 50 feet away has time to react and vanish. A squid detecting a threat at 5 feet away does not. The sleeper shark's entire hunting strategy is about getting to 5 feet. Its electrical sense, through sensory pores in the snout called ampullae of Lorenzini, can detect the tiny electrical field produced by a squid's muscle activity from around 6 to 10 feet away. The shark doesn't need to see the squid. It follows the electrical signal through the water, like a signal from a tracking device, adjusting its direction without increasing speed, staying below the threshold that would trigger the squid's own pressure detection system. When the shark crosses into strike range, everything changes. The jaw opens with a motion so compact and fast that high-speed video analysis clocks it at under 1/10 of a second. The suction the opening jaw creates pulls water inward, and anything in the water in front of the shark comes with it. Against soft-bodied prey, this suction-strike combination is usually decisive. Against a giant squid, it starts a fight. The squid's first response to contact is to wrap. Arms come forward, tentacles extend, suckers clamp wherever they land. The shark is already committed to the bite, and now both animals are attached to each other in the dark. The shark pulling one direction, the squid pulling the other, both using every structure they evolved for exactly this kind of contest. What those first seconds of contact look like, no human has ever witnessed directly. But the injuries both animals carry out of these encounters give scientists a detailed picture of what happens when neither one lets go. And one detail from that picture changes everything scientists thought they knew about squid behavior. Every prey animal on Earth has a primary escape strategy. Rabbits run, octopuses hide, fish form schools to confuse predators. The giant squid's first and most powerful escape option is its jet, a burst of water ejected from the mantle that can launch it backward at speeds that make it nearly impossible to track. So why does evidence consistently show that giant squids don't just run from sleeper sharks? The scar patterns on sharks answer that question directly. If giant squids fled every encounter, the sharks would occasionally lose grip and come away unmarked, or with only minor contact marks. Instead, researchers find deep, multiply-layered scar clusters on sharks that indicate sustained, forceful contact maintained over time. You don't get 40 sucker ring scars on a single shark from 40 brief accidental touches. Those scars come from an animal pressing hard and holding on. The giant squid fights. Marine biologist Steve O'Shea, one of the foremost giant squid researchers of the last 30 years, described the animal's aggression in terms that surprised the broader scientific community when his observations were published. Squids brought to the surface alive, even in the desperate and disorienting conditions of capture, consistently attacked rather than withdrew. They bit at net lines. They wrapped arms around cable housings. They drove beaks into steel sampling equipment. The instinct to engage a threat rather than escape it appears deeply embedded. Scientists debate why this evolved. One leading argument focuses on energy. A jet-propelled escape consumes enormous energy. The mantle has to rapidly fill with water and then expel it at force, and doing this repeatedly drains the squid's reserves in a short time. If a squid encounters multiple predators in a single hunting session, spending full escape energy on the first one could leave it unable to respond to the second. Fighting may be the energy-efficient choice when a full escape isn't guaranteed. Another argument focuses on size. A mature giant squid is not small. It weighs several hundred pounds and carries nearly 50 gripping, biting contact points across its arms. Against a predator that approaches slowly and commits to a bite, wrapping those arms around the predator's head is a viable counter-strategy. It disrupts the shark's sensory ability, physically blocks the jaw, and in some cases may cause enough discomfort to force the shark to release. There is documented evidence this works. Researchers have found sleeper sharks with healed but significant injuries near the snout and around the eyes, areas where squid arms would concentrate during a defensive wrap. A shark with damaged sensory organs is a less effective hunter. The squid's fight-back strategy, if it succeeds even partially, degrades the shark that attacked it and makes that same shark less dangerous in future encounters. The deeper implication of this behaviour is significant. The giant squid and the sleeper shark are locked in a relationship that shapes both of them. The shark's hunting method evolved partly in response to the squid's ability to detect approach. The squid's fighting instinct may have evolved partly in response to the shark's ambush technique. Each animal drives the evolution of the other over thousands of generations. Scientists call this coevolution, where two species shape each other through their conflict. And in the Midnight Zone, this coevolution produced something wilder than anyone expected. Because the squid has a weapon nobody anticipated, and the shark has no defense against it. In total darkness, light means food. Every animal that has evolved to survive in the deep ocean understands this at a biological level. Bioluminescence, the ability to produce light through a chemical reaction in living tissue, is the most common form of communication, hunting, and survival in the Midnight Zone. Down there, an estimated 90% of all sea life produces some form of biological light. The darkness is not empty. It flickers constantly with signals. The sleeper shark does not produce its own bioluminescence. Its body carries no light-generating organs, but its skin does something that researchers only recently began to understand fully. Under certain wavelengths of light, the skin of a Pacific sleeper shark produces a faint glow. Scientists studying deep-sea shark bioluminescence published findings in 2021 confirming that several species of deep-sea sharks, including close relatives of the sleeper shark family, exhibit what they call biofluorescence, meaning they absorb certain light and re-emit it at a different wavelength. The glow is subtle, barely visible even with sensitive instruments. But in an environment where any light source is a potential signal, subtle is enough. Here is the hypothesis that some researchers find compelling and others argue against intensely. In the Midnight Zone, one of the giant squid's primary prey items is mid-sized fish and smaller squid species, many of which are bioluminescent. The squid hunts by detecting faint movement and faint light. A source of faint light in the water, drifting slowly, could read to the squid's sensory system as a potential meal. If the sleeper shark's biofluorescent glow registers as a prey signal, the giant squid might actually approach the shark rather than waiting to be found. The squid would be initiating the encounter, moving toward what it interprets as a target, only to find itself suddenly within the shark's electrical detection range. This would explain a detail in the scar evidence that puzzled researchers. On some sharks, the suckering scars begin at the snout, the front end, the part of the shark facing toward the squid during an approach. A squid attacking from the front makes sense if the squid came toward the shark and struck first, perhaps believing it was seizing prey. The shark's response, a bite from the jaw directly below the snout, would then represent a counterattack from an animal that suddenly had a giant squid wrapped around its face. The scenario, if accurate, means the squid initiated these encounters. The apex predator of the Midnight Zone was pulled in by a trap it didn't recognize as one. Scientists are cautious about this hypothesis because it relies on assumptions about how the squid interprets light signals, something hard to test. The squid cannot be interviewed. Its sensory experience in the deep cannot be directly measured. But the behavioral evidence is consistent enough that the hypothesis remains active in the scientific literature. What is agreed upon is that bioluminescence plays a central role in nearly every hunting encounter at these depths. Light, or the absence of it, decides who eats and who gets eaten. And the squid's own relationship with light turns out to be far more sophisticated than anyone realized, involving a trick the squid pulls mid-fight that could change the outcome of any encounter with any predator, including one it never had any warning was coming. Hold a plastic water bottle sealed with air inside and take it to the bottom of a swimming pool. You can feel the pressure compress the bottle as you descend. By the deep end, it is visibly deformed. Now imagine descending not 12 feet but 6,000. A sealed bottle brought to that depth would be crushed down to a fraction of its original size. Every air-filled cavity gets compressed under pressure. Lungs, air bladders, sinuses. Any space inside an animal that contains gas becomes a structural liability as depth increases. This is why most surface-adapted animals cannot survive in the deep ocean. Their bodies contain cavities that the pressure would collapse. The giant squid has almost no gas-filled spaces in its body. This is the central adaptation that allows it to exist at depths that would destroy most large animals. Its internal structure is almost entirely solid tissue, or tissue permeated with a liquid called coalomic fluid. The fluid filling its body cavities is essentially incompressible, the same physical property that makes water itself resist compression. Pressing on water doesn't shrink it the way pressing on air does. A fluid-filled cavity under pressure stays the same size. This means the squid's body has no weak points for pressure to exploit. The one major exception is the squid statocysts, organs used for balance and orientation, which contain small solid structures called statoliths. Scientists who have brought giant squids up from depth to the surface have observed that rapid pressure change can damage these organs, disrupting the squid's ability to orient itself. This is part of why squids brought up alive in fishing nets often appear confused and uncoordinated. The journey from extreme pressure to near zero pressure in a short time disorients them physically. For the squid living at depth, though, the pressure is never a problem. Its body is calibrated to it. The chemical solution adds another layer. Giant squids have high concentrations of ammonium chloride dissolved throughout their tissues. This compound is lighter than seawater, which gives the squid a form of buoyancy at depth. The squid doesn't need to actively swim to stay at a given depth. It is naturally close to neutral buoyancy, meaning it neither sinks nor floats without effort. This allows it to hover almost motionless while hunting, conserving energy, waiting. The sleeper shark's pressure adaptation uses a different chemistry, as covered earlier, but both animals arrive at the same result: functional biology at depths that should be fatal. What makes this scientifically striking is that these adaptations evolved separately in two very different animal lineages. The squid is a mollusk, related to snails and clams. The shark is a vertebrate, related to every fish and eventually to every land animal on Earth. Two completely separate evolutionary trees, facing the same pressure problem, arriving at functional chemical solutions. Deep-sea biologists use this as a case study in what they call convergent evolution, where unrelated animals evolve similar solutions to the same environmental challenge. The pressure zone these animals share is brutal, unlivable for most life, and that extreme environment is precisely what makes the giant squid so hard to study and so poorly understood. The science of how it actually behaves, defends itself, and attacks during a real encounter relies heavily on indirect evidence. And the most indirect and most revealing piece of evidence turns out to be something the squid produces that scientists can track even long after the fight ends. The ink cloud is the giant squid's most famous trick, and almost everyone pictures it wrong. In popular imagination, a squid squirts ink to create a smoke screen, a dark blob that hides the squid while it escapes. That picture captures one function but misses a deeper one that researchers have found to be far more significant, especially against a predator like the sleeper shark that barely relies on vision. Giant squid ink is not just pigment, it is a chemical cocktail. The primary component giving the ink its colour is melanin, the same pigment that gives human skin its colour. Melanin is what creates the visual cloud. But dissolved into the ink alongside the melanin are two compounds with very different purposes. The first is tyrosinase, an enzyme that interferes with chemical receptors. The second is dopamine, a signalling chemical that disrupts nerve function in animals that encounter it in concentrated form. Against a predator using vision, the visual cloud works as expected. Against a predator using chemical senses to navigate, which describes almost every deep-sea hunter. The chemical components of the ink cloud are the real weapon. Sharks navigate partly through chemoreception, detecting dissolved chemicals in the water. Their nostrils are not for breathing. They are chemical detectors of extraordinary sensitivity, capable of sensing blood diluted to 1 part per million in open water. When a giant squid releases its ink cloud, the tyrosine and dopamine flood a zone of water several feet across. A shark's chemical sensing system, suddenly flooded with a concentration of tyrosine, experiences what researchers describe as temporary chemical overload. The sensory signal the shark was following, the chemical trace of the squid's own body fluids, gets buried under the ink's compounds. The squid disappears from the shark's chemical map. Researchers studying squid ink chemistry published a study analysing the specific compounds in several squid species, including the giant squid's closest relatives, since getting intact ink samples from deep-sea giant squids is extremely difficult. The findings confirmed that the tyrosine concentration in large squid ink is high enough to produce measurable interference with the chemoreceptor function in laboratory shark tissue samples. There is also evidence the ink cloud affects the shark's lateral line system. The sudden fluid displacement of a large ink cloud, ejected under pressure, creates a pressure pulse in the surrounding water. The lateral line of a shark, which detects exactly these pressure changes, receives a false signal. The pulse mimics the signature of a large object moving suddenly in one direction. The shark's reflexive response is to orient toward that signal, which directs it toward where the squid was, while the squid jets in the opposite direction. The cloud is a decoy, a chemical disruptor, and a sensory misdirection device simultaneously. Against a shark relying on vision, this would offer modest benefit in an environment with almost no light anyway. Against a shark relying on chemical sensing and pressure detection, the ink cloud is a precision counter. It targets exactly the systems the sleeper shark uses to hunt. That the giant squid produces exactly the right chemicals to interfere with exactly the shark's hunting systems could be coincidence. Scientists who study predator-prey coevolution tend to doubt coincidence at this level of precision. Something even harder to explain is what the squid does with its skin during a fight, and once you hear it, the idea that these animals are just mindlessly attacking each other becomes very difficult to believe. A sleeper shark washed up on a beach in Iceland is not a gift, it is a hazard. The flesh of the Greenland sleeper shark, the Atlantic relative of the Pacific sleeper shark and a member of the same broad family, is toxic to humans and to most animals that attempt to eat it fresh. The toxicity comes from high concentrations of trimethylamine oxide and its breakdown products in the shark's tissues, specifically a compound called trimethylamine that forms as the flesh decomposes. In sufficient quantities, this compound acts as a neurotoxin, causing a specific set of symptoms in mammals: an intense burning sensation in the mouth and throat, disorientation, loss of muscle control, and in large doses, incapacitation. Sled dogs fed fresh Greenland shark have lost the ability to walk. Humans who have eaten unprocessed Greenland shark have reported effects compared to severe drunkenness. The Icelandic traditional food called hakal, which is Greenland shark meat that has been buried and dried for up to 6 months, is the processed result of removing this toxicity through time and decomposition. Fresh, the shark is essentially poisoned meat walking around in the ocean. The Pacific sleeper shark carries similar compounds in its tissues, though the concentration and exact chemistry differs somewhat between species. The relevant question for the giant squid conflict is whether this toxicity plays any role in their interactions. The honest scientific answer is probably not directly. The toxicity affects mammals more severely than it affects most marine animals. A giant squid encountering a sleeper shark is not biting off and swallowing pieces of the shark in a way that would expose it to toxic tissue. The squid's beak interactions during a fight are more about puncture and grip than consumption, but the toxicity matters for understanding the sleeper shark's position in the deep sea ecosystem. The fact that this animal's flesh is chemically defended means it has fewer predators of its own. Sleeper sharks grow old partly because relatively few things can or will eat a fully healthy adult. The orca, or killer whale, is one of the few confirmed predators of sleeper sharks. Researchers documented orca attacks on Pacific sleeper sharks off Alaska, and the behaviour was striking. The orcas targeted the shark's liver specifically, discarding the rest of the body. The liver of a sleeper shark is enormous, sometimes up to a quarter of the shark's total body weight, and it contains high-quality fats without the same neurotoxic compounds found in the muscle tissue. Even predators smart enough to hunt a toxic shark know which part to eat. For the giant squid, the encounter with a sleeper shark is not about eating it. The squid doesn't benefit from consuming shark tissue. The fight, when it happens, is survival. Either the squid escapes or it doesn't. The shark's toxicity is irrelevant to that equation. But the sleeper shark's long life, protected partly by its toxic flesh, means a single shark can accumulate decades of encounters with giant squids and carry the scar record of all of them. The oldest Greenland sleeper sharks studied have been estimated at over 400 years old. Multiple studies suggest Pacific sleeper sharks regularly exceed 150 years. 150 years of hunting in the midnight zone. 150 years of encounters recorded on its skin. The oldest shark scientists have examined carry scar tissue laid over scar tissue, evidence of a lifetime of conflicts in the dark. What those scars reveal about the shark's very long life is something that changes how you see the entire deep ocean. The beak is the last part of the squid to surrender. Every other structure, the arms, the mantle, the soft tissue, breaks down quickly once inside a stomach. The acid environment of any predator's digestive system handles soft material efficiently, but the squid's beak is made of chitin, the same dense biological material found in insect exoskeletons and crab shells. Chitin resists acid. It resists mechanical breakdown. A squid beak placed in stomach acid does not dissolve in hours or days. It persists for weeks, months, sometimes longer. This fact is what made squid beaks the key piece of evidence in tracking these predator-prey relationships. Scientists could open a stomach and find a beak that had been there for a long time, and still extract meaningful information from its size and shape about the squid that owned it. But the beak's durability has another consequence that researchers discovered with some shock. A squid beak inside a predator's stomach does not simply sit there passively. It is a hard, pointed, curved object surrounded by soft tissue walls. And when the stomach contracts during digestion, the stomach walls press against everything inside them, including the beak. A squid beak under repeated gastric contraction can puncture stomach tissue. Researchers examining the stomach linings of sleeper sharks that had recently ingested giant squids found exactly this. Fresh puncture wounds and cuts in the stomach mucosa, the soft inner lining of the stomach, in patterns that match squid beak edges and tips. Some of the wounds were clearly new, with minimal healing. Others showed partial scarring, suggesting the damage had occurred during a previous meal and the shark's tissue had been trying to repair itself. In some specimens, the damage extended deeper than the mucosa layer into the muscular stomach wall itself. For a human digestive surgeon looking at those specimens, the description would be recognizable. A foreign body capable of causing repetitive pressure injury in a confined muscular space produces exactly the kind of wound pattern found in those sharks. The beak was slowly working against the stomach wall, with every digestive contraction. Now add the detail introduced earlier, that stomach injuries in sleeper sharks carrying fresh beak evidence were observed to be actively bleeding in recently deceased specimens. A shark's stomach wall bleeding from beak punctures means a live squid beak was causing ongoing injury during digestion. The squid's defenses continued working even after the squid itself was dead. The stomach injury research changed how scientists thought about the cost of hunting giant squids. Every successful catch carries a price. The shark wins the fight and swallows the squid. Then the squid's beak spends the next several days slowly damaging the shark's stomach lining. Sharks with heavy beak accumulation in their stomachs showed higher rates of gastric scarring than sharks eating other prey types. Long-term repeated giant squid consumption may cause chronic digestive damage in sleeper sharks. This means the squid exacts a cost even in defeat. The shark pays for every successful hunt with tissue damage it carries for months. The squid's beak, essentially the squid's last act, keeps injuring the predator long after the fight ended. For an animal that has been hunting giant squids for potentially hundreds of years, the accumulated gastric damage must be significant, and it raises a question scientists have only recently started exploring. Does this cost change the shark's hunting decisions? Does a shark with a heavily scarred stomach target giant squids less frequently? The data is still being gathered. But the emerging answer is darker and stranger than a simple yes or no. Remove the top predator from any ecosystem, and the effects ripple down through every layer below it. Everyone knows this about wolves in Yellowstone or sharks on coral reefs. Remove the wolves, the elk overgraze, the riverbanks erode, the songbirds disappear. A single species at the top holds together everything underneath it. Giant squids are not at the top. They are hunted. But they play the equivalent structural role in the midnight zone, from below rather than above. Scientists studying deep-sea food webs discovered that giant squids function as what ecologists call keystone prey. A keystone prey species is one whose abundance is so significant and whose body provides such a concentrated source of nutrition that multiple predator species depend on it. Remove the keystone prey, and the predators that relied on it face immediate nutritional crisis. Some adapt, others decline. The ecosystem reorganizes around the loss. In the midnight zone of the Pacific and Atlantic, giant squids provide massive caloric packages to sperm whales, sleeper sharks, and several species of large-beaked whales. A single giant squid, weighing several hundred pounds and packed with protein and fat, represents an enormous meal by deep ocean standards. The effort required to hunt one is offset by the return. Sperm whale populations in the Pacific have been estimated to consume millions of pounds of giant squid annually. This consumption is so significant that the nitrogen and other nutrients in squid tissue, transported to the surface when whales defecate after deep dives, measurably fertilize surface water plankton blooms. The squid's body, eaten at depth, contributes nutrients that cycle back to the sunlit surface zone and feed the microscopic life that anchors the entire ocean food chain. Sleeper sharks feed more quietly, in smaller individual amounts, but across a vast geographic range and across centuries of individual lifetimes. A single long-lived Pacific sleeper shark may consume thousands of giant squids over its lifetime. Multiplied across the sleeper shark population, the energy transfer from giant squid to shark is a significant flow through the deep ocean's nutrient budget. The giant squid, as prey, connects the surface world to the midnight zone through its predator's behavior. Sperm whales carry squid nutrients upward. Sleeper sharks cycle them laterally across vast deep-sea territories. Giant squid populations themselves depend on a food supply one step below them. They eat mid-sized fish, other squid species, and deep-sea shrimp. These animals in turn eat smaller organisms. The giant squid's role sits in the middle of a chain that extends from plankton at the surface all the way down to the bacteria that break down dead tissue on the seafloor. The squid is a major link, not at the top or bottom, but load-bearing in the middle. When anything disrupts giant squid populations, the disruption travels in both directions along that chain. Predators above lose a key food source. Prey below face reduced pressure. The ecosystem shifts. This is why researchers studying the giant squid-sleeper shark relationship are careful to frame their work not just as a fascinating predator-prey story, but as essential ecology. Understanding who eats whom in the midnight zone, and how often, and how efficiently, is baseline knowledge for understanding how the deep ocean functions as a living system. And one comparison that researchers keep returning to, the one that first made these midnight zone battles visible to the outside world, involves an animal far larger than any sleeper shark. one that leaves evidence of the same squid battles on its skin and carries it to the surface for scientists to see every time it breathes. A sperm whale surfaces in the open Pacific, breathes, and rolls slowly before diving again. At 30 feet from the surface, researchers in a small boat photograph its skin through long lenses. Later, back in the lab, those photographs reveal something that tells a story the whale cannot. Across the whale's head and upper body, circular scar rings, dozens of them, some fresh and slightly raised, others faded silver-white, old enough to have been there for years. Every one of them matches, in shape and diameter, the sucker ring scars documented on Pacific sleeper sharks. The same squid left marks on both of them. Sperm whales are the most famous giant squid hunters on Earth, and unlike sleeper sharks, they hunt at speed. A sperm whale can dive to depths of over 7,000 feet, which makes it one of the deepest diving mammals known to science. It descends at an angle, clicks loudly through the water using a biological sonar system of almost unbelievable precision, and locates giant squids by the reflection of its own sound off their bodies. Then it rushes them. The sperm whale's hunting method is the opposite of the sleeper shark's. Where the shark uses stillness, electrical detection, and a slow closing approach, the whale uses speed, sound, and decisive attack from a distance. Both strategies succeed. Both result in whale and shark stomachs full of squid beaks. Both result in sucker ring scars on the predator's skin. Researchers comparing scar patterns on sperm whales and sleeper sharks found the clustering almost identical. Front heavy, concentrated around the head and snout, sparse or absent near the rear body. The same tactical picture. The squid wraps forward, targeting the predator's head, and the predator keeps its propulsion system clear. This parallel is significant for understanding the giant squid's defensive behavior. When two completely different predators, one a slow ambush specialist, one a fast sonar-guided charger, both end up with front body squid scars, the explanation lies in the squid, not in the predators. The squid is consistently choosing to wrap forward against any large threat. The behavior is fixed enough to produce identical scar patterns across species that hunt completely differently. The scale difference between the two predators also reveals something about the squid's fighting capacity. A sperm whale weighs over 40 tons, the same as 8 African elephants. Its bulk alone exceeds the squid's by many times over, and the squid still fights it. These are grip marks from an animal pressing hard against something 40 times its weight. A sperm whale with fresh deep squid scars near its eyes has experienced a squid attempting to disable its sonar-producing structures. Whether this strategy ever succeeds against a whale is unknown, but the attempt is recorded in tissue. Scientists have also noted that a small percentage of sperm whales carry healed but deep scars from encounters where the squid did serious damage. One specimen examined off the Azores had scar tissue near the lower jaw, consistent with sucker rings the size of a man's fist, from a squid at maximum known size. The giant squid fought a sperm whale hard enough to leave a scar the whale carried for years. What makes the squid capable of this at a biological level is something scientists only fully understood when they examined its internal anatomy in detail. And one system inside the squid's body is so strange, so unlike anything in familiar animal biology, that it makes the giant squid feel like a creature from a completely different world. A giant squid has 3 hearts, and none of them pump red blood. The blood of a giant squid is blue. Genuinely, visibly blue, the colour of a clear sky on a cold morning. This is not a metaphor or an approximation. When researchers bring up giant squid tissue and it bleeds, the blood is blue. The reason comes down to chemistry. Human blood is red because of hemoglobin, a protein that uses an iron atom to carry oxygen through the bloodstream. Iron gives hemoglobin its red colour. Giant squid blood uses a completely different oxygen-carrying protein called hemocyanin. Instead of iron, hemocyanin uses copper. Copper-based molecules, when oxygenated, appear blue. When the oxygen is released, the blood turns nearly colourless. The cycle of blue to clear and back to blue happens with every circuit through the squid's circulatory system. Hemocyanin is less efficient than hemoglobin at delivering oxygen under normal conditions. In warm, oxygen-rich water, it would be a disadvantage. But in the cold, oxygen-lower water of the deep ocean, hemocyanin performs better. It releases oxygen more readily at the pressures and temperatures of the midnight zone. The squid's blood chemistry is optimized for exactly the environment it lives in. This is why giant squids are so sensitive to warm water. If ocean temperature rises by even a few degrees in deep zones, the squid's hemocyanin becomes less effective at delivering oxygen to tissues. The squid essentially starts suffocating in water that is still technically oxygenated. Researchers studying giant squid distribution have flagged this as one of the reasons these animals are found only in cold ocean zones. The three-heart system exists to overcome one of hemocyanin's limitations: low-pressure delivery. Hemocyanin requires stronger pumping force to move oxygen efficiently through the body than hemoglobin does. The giant squid solution is to not rely on a single heart. It has one main heart, called the systemic heart, that pumps blood to the body. It has two smaller hearts, called branchial hearts, positioned directly beside the gills. Each branchial heart pulls blood through the gill tissue separately, oxygenating it there, before sending it to the main heart to be distributed. Three hearts working together maintain the blood pressure and oxygen delivery the squid needs to function at depth, at speed, and during the intense physical exertion of a fight. During a battle with a sleeper shark, the squid's three hearts are working at maximum capacity. The muscle activity of wrapping arms, driving tentacles, and jetting water through the mantle all demand oxygen at a high rate. The branchial hearts accelerate. The systemic heart increases its output. Blue blood cycles faster. From the outside, you would see nothing of this. The squid's internal physiology during combat is invisible. But dissections of squids found recently dead, some with injuries consistent with shark encounters, allowed scientists to examine the cardiovascular system under stress conditions. The branchial hearts in injured specimens showed hemorrhaging, evidence they had been working at extreme output before death. These animals are fighting at their biological limits. The squid's alien biology, its blue blood, its three hearts, its copper-based oxygen system, did not arise randomly. Every feature was shaped by millions of years of pressure, cold, darkness, and the relentless need to survive encounters with predators that have been hunting it for just as long. And the predator's biology, across equally vast stretches of time, holds its own record of exactly how long that hunt has been going on. In 2016, a research team caught a Greenland sleeper shark and took a small tissue sample from its eye lens. The lens of a shark's eye, like the rings inside a tree trunk, adds layers as the animal grows. Older layers sit at the centre, newer layers form around the outside. By measuring the ratio of carbon isotopes in the innermost layers, scientists can estimate when those layers formed. The result from that one shark came back at approximately 392 years old. Give or take 120 years due to measurement uncertainty, the animal was born somewhere between the 1500s and the early 1600s. That means this living shark existed before the Pilgrims landed in America. The Greenland sleeper shark is now the longest-lived vertebrate animal known to science. The Pacific sleeper shark has been harder to age precisely, but tissue and growth rate studies place its maximum lifespan comfortably above 150 years, possibly approaching 200. These numbers reshape everything about how you interpret the scar evidence on their bodies. A sleeper shark that lives 200 years and begins encountering giant squids at sexual maturity, around 150 years into its life based on current estimates, has a full century and a half of hunting experience behind every single encounter. Each fight is not an isolated event. It is one episode in a multi-generational hunting career that outlasts entire human lifetimes. Scientists studying the Pacific sleeper shark's growth rate discovered why this extreme lifespan is possible. These animals grow extraordinarily slowly, adding roughly 1 centimetre in length per year. A 10-foot shark is already decades old. A 20-foot shark may be well over a century. Slow metabolism, cold water, minimal energy expenditure. The biology that makes the sleeper shark a plodding hunter is the same biology that makes it nearly immortal by animal standards. This long life creates a concentration of hunting experience that no other deep-sea predator can match. An old sleeper shark has survived encounters that killed younger individuals. It has encountered squid of every size, every level of aggression, every defensive strategy the squid can deploy. Its behaviour in any given hunt reflects that accumulated history, even if we cannot directly observe the learning process. There is a parallel here worth pausing on. The oldest Greenland sharks alive today were already mature adults during the American Revolution. They were hunting in the dark Atlantic while George Washington crossed the Delaware, while the Wright brothers flew at Kitty Hawk, while the first moon landing happened. Through all of it, in complete darkness and silence, they kept hunting giant squids and adding sucker ring scars to their skin. The squid they hunt today is the same species their ancestors hunted centuries ago. The beak chemistry is identical. The sucker ring diameter falls in the same range. The fight happens in the same dark pressure zone. 2 animals locked in a conflict older than any living human institution. One of them keeps a permanent record of every encounter it survived. The other keeps no record at all, because squids live fast and die young, rarely surviving more than 5 years. A 150-year-old shark versus a 2-year-old squid, with centuries of evolved tactics on one side and raw biological power on the other. The daily environment where this plays out is stranger than the fight itself. Every day, without fail, one of the largest migrations on Earth happens completely out of sight. At dawn, hundreds of millions of small fish, squid, shrimp, and other sea creatures descend from the upper ocean. They drop from depths of around 600 feet, where they spent the night feeding, down to around 3,000 feet, where daylight cannot reach them. At dusk they rise again, ascending to feed in the darkness of the upper ocean before the cycle repeats. This vertical migration happens across every ocean on Earth simultaneously. Scientists discovered it during World War II when military sonar equipment, designed to detect submarines, kept picking up a false bottom in the ocean that moved. The signal rose at night and sank during the day. Researchers eventually identified it as a massive layer of marine life, dense enough to reflect sound the way the seafloor does. They named it the Deep Scattering Layer. The discovery stunned naval commanders who had spent years dismissing sonar readings they assumed were equipment failures. The false bottom was real. It was alive. The layer moves 2 miles or more vertically every day. If you converted that vertical distance to a horizontal road, it would be like driving from one side of a major city to the other, every day, without stopping, for an entire lifetime. Both giant squids and sleeper sharks follow this migration, and that following behaviour is the primary reason the 2 animals overlap in depth at all. Giant squids hunt the deep scattering layer from below, rising into it at night to chase the small squid and fish that rise with it, then descending as the layer sinks at dawn. Their vertical range tracks the layer's movement across a daily cycle. Sleeper sharks patrol the lower boundary of the layer, waiting where the migrating animals concentrate as they descend. A scientist named Matteo Bernardi, working on deep-sea predator tracking in the Pacific, described the layer as a moving buffet that organizes the entire deep ocean's predator behavior. Predators don't need to search randomly. They follow the layer and find prey concentrated into a predictable band. This predictability is what makes the sleeper shark's slow hunting strategy viable against the giant squid. The shark does not need to chase. It stations itself in a zone where squids reliably appear, at predictable depths, at predictable times. The squid descends into the shark's territory, focused on its own prey, and the shark closes in from below with its electrical senses leading the way. The deep scattering layer also explains the geographic range of these conflicts. Anywhere the layer is dense, squids concentrate. Wherever squids concentrate, sleeper sharks appear. The correlation between layer density and squid-shark interaction evidence, measured in scar frequency on sharks from different regions, is strong enough that researchers use layer maps to predict where conflict is most likely to occur. At 3,000 feet, in absolute darkness, two animals riding the same daily current find each other with regularity. One descended following its prey, the other ascended following its dinner. The layer brought them together. And something else uses that same layer, something so bizarre and so relevant to the giant squid's survival that scientists spent decades arguing about whether it was even real. And when they finally confirmed it, the implications for how the squid defends itself changed everything. Silence in the deep ocean is a misleading idea. Sound travels faster through water than through air, and it travels much farther. A blue whale's call can propagate across entire ocean basins. The clicking of a sperm whale's sonar at a depth of several hundred feet produces a sound pressure level loud enough to stun or disorient prey at close range. The deep ocean is acoustically rich in ways the human ear, designed for air, would struggle to process. Giant squids have no ears. They have no structure resembling an ear at all. Scientists studying cephalopod sensory biology spent considerable time assuming this meant squids were deaf, unable to detect sound in any meaningful way. That assumption turned out to be wrong. In the early 2000s, a team of marine biologists at the Woods Hole Oceanographic Institution designed an experiment to test whether squid and octopus species could detect low-frequency sound. They exposed squid specimens to controlled sound pulses at different frequencies and intensities. At very low frequencies, below 200 Hz, the squid showed clear physiological and behavioral responses. The statocysts, the balance organs inside the squid's head containing small solid particles, vibrated in response to low-frequency sound. The squid's body picked up sound not through hearing in the conventional sense, but through physical resonance of its internal structures. This matters for the sleeper shark encounter in a specific way. The sleeper shark's body moving through water, even at its extremely slow 1 mile per hour pace, produces low-frequency pressure waves. These waves propagate outward through the water. The giant squid statocysts, sensitive to exactly this frequency range, can potentially detect those waves from a significant distance. If the squid detects the shark's approach through low-frequency resonance before the shark's electrical sensing range reaches the squid has a warning window, a small one, possibly only a few seconds, but potentially enough to initiate an escape jet before the shark closes to strike distance. This creates a race between two sensory systems: the shark's electrical detection, effective at 6 to 10 feet, the squid's acoustic detection, possibly effective at 30 to 50 feet. If the squid detects the shark's pressure wave at 40 feet and jets, the shark loses the encounter. If the shark somehow closes from 40 feet to 6 feet without triggering the squid's resonance response, the shark wins. The margin is razor thin. The squid's statocyst response time from vibration detection to neural signal to muscle contraction takes roughly 1/5 of a second. In that 1/5 of a second, a shark travelling even at 1 mile per hour covers about 3 inches. At strike distance, 3 inches is the difference between a clean miss and a successful bite. Scientists debate whether the sleeper shark's near-motionless approach is specifically calibrated to produce minimal low-frequency disturbance. The data is suggestive. A faster-moving shark would generate stronger pressure waves. The sleeper shark's extreme slowness may suppress the pressure signal to the point where the squid's statocyst response threshold is not triggered until the shark is already close enough to strike. Every piece of the sleeper shark's hunting method seems designed, through millions of years of selection, to stay below the squid's detection capabilities until the last possible moment. and the squid has one more counter-strategy waiting, one that works in the fraction of a second between detection and contact. It is visible, it is fast, and against almost any other predator, it ends the fight instantly. A giant squid in the open water can turn its skin into a light show. Embedded across the entire surface of a squid's mantle and arms are millions of tiny colour-producing cells called chromatophores. Each one is a small sac of pigment connected to a muscle fibre. When the muscle contracts, the sac stretches flat and the colour inside becomes visible. When the muscle relaxes, the sac shrinks back to a tiny pinpoint and the colour disappears. A squid controls these cells through direct nerve signals, and it can cycle them across its entire body in patterns that change in under 1/10 of a second. The result is something that looks like a ripple of colour moving across a living surface, or a sudden full-body flash of intense pigmentation, or a strobing pattern that alternates between light and dark across different sections of the body simultaneously. Scientists studying squid chromatophores in laboratory settings have documented patterns of extraordinary complexity. Waves of colour that move from head to tail, rings that expand outward from a central point, alternating stripes that shift at frequencies faster than the human eye can comfortably track. The chromatophore system is one of the fastest and most precise biological displays in the animal kingdom. In the deep ocean, where the only light comes from bioluminescent sources, the chromatophore display operates differently than it does in lit laboratory tanks. Deep-sea chromatophores can interact with bioluminescent light in ways that create local flashes. A squid encountering a bioluminescent flash from another animal, or producing its own through photophores, can potentially amplify or redirect that light across its chromatophore layer. The defensive application during a shark encounter is a hypothesis that remains contested, but the logic is compelling. A sleeper shark closing to strike distance is operating on electrical sensing. Its visual system, compromised by eye parasites and the darkness, contributes little information to the hunt. Against a visually guided predator, a sudden full-body chromatophore flash might startle or confuse. Against an electrically guided predator like the sleeper shark, the same flash does little visually. Where it may matter is in the electromagnetic domain. Chromatophore contraction involves rapid coordinated muscle activation across millions of cells simultaneously. That level of synchronized muscle activity produces a detectable electrical event. A sudden full-body chromatophore activation could generate an electrical pulse strong enough to interfere with the shark's electrical sensing system at the moment of contact, producing a burst of electrical noise that drowns out the directional information the shark needs to aim its bite. Researchers have measured electrical activity from rapid chromatophore displays in related squid species and confirmed measurable pulses. Whether those pulses are strong enough to disrupt a shark's sensory system at the distances and intensities involved in an actual encounter remains to be tested. What is certain is that the squid's chromatophore system is more than decoration. Every high-speed biological system evolves under pressure. Something uses it. Something benefits from it enough to maintain it across millions of years of evolution. The darkness of the midnight zone hides that something from us. But the physical record of these encounters, scattered across the skin of old sharks and old whales, keeps building a picture of a conflict far more sophisticated than anyone first imagined. Sophistication requires the right environment, and the environment these battles happen in has its own extreme biology. Drop a thermometer to 3,000 feet in the North Pacific, and it stops falling fast somewhere around 35 degrees Fahrenheit. That is 3 degrees above the freezing point of fresh water. Salt water freezes at a lower temperature, so the ocean at these depths stays liquid. But it is cold enough to kill most air-breathing animals within minutes of exposure. A human swimmer in 50-degree water loses consciousness within 1 hour. In 35-degree water, the timeline compresses sharply. Cold shock, the involuntary gasp reflex triggered by sudden immersion in cold water, strikes within seconds. Muscle control begins failing in 3 to 5 minutes. Loss of consciousness follows shortly after. Without intervention, death occurs before the 15-minute mark. The biology of warm-blooded mammals and birds depends on maintaining a core body temperature around 98 degrees. The gap between 98 and 35 is enormous. Maintaining that gap against the cold requires continuous energy expenditure, and in water, which strips body heat 25 times faster than air, the demand becomes overwhelming almost immediately. Cold-blooded animals face a different problem. Their metabolic rate drops with temperature. At 35 degrees, the chemical reactions inside a cold-blooded animal slow significantly. Muscle response time increases, digestive efficiency drops, neural processing slows. An animal adapted to warm water and suddenly placed in cold water becomes sluggish and ineffective. Sleeper sharks solved both problems simultaneously. Their body temperature matches the surrounding water exactly. They generate no internal heat. This eliminates the energy cost of thermal maintenance, and the chemical systems inside their cells are calibrated to function at near-freezing temperatures. Their enzymes operate efficiently at temperatures that would make most animals sluggish. Their muscles contract with full force at 35 degrees. Their nerves transmit signals at full speed. The cold is not a challenge for the sleeper shark. The cold is home. Giant squids share this adaptation. Their hemocyanin-based blood, as discussed in the chapter on their biology, functions better in cold water. Their cell chemistry, like the sharks, is tuned to work well in conditions that would disable most life. This shared cold water adaptation is part of what makes these two animals the dominant large predators of these deep zones. Most competitors are locked out by temperature. Warm water species cannot sustain function at these depths. Even sperm whales, which dive into the midnight zone to hunt squids, cannot stay there indefinitely. Their warm-blooded physiology burns through oxygen faster in cold water, and they must surface to breathe within roughly 90 minutes of a deep dive. The sleeper shark never needs to surface. It never needs to breathe air. It lives permanently at depth, in the cold, with unlimited bottom time. In any competition for the same prey, it has a fundamental advantage over every air-breathing predator on Earth. Consider the contrast directly. A sperm whale dives into the midnight zone, hunts under extreme physiological stress, and must ascend within 90 minutes or risk oxygen depletion. A sleeper shark can spend weeks at 3,000 feet without ascending at all. Every squid the whale drives downward during a chase enters water. The shark already controls and has controlled for potentially 2 centuries. The whale visits, the shark lives there. And yet the giant squid holds its position in this environment, competing with a cold-adapted predator that has centuries of experience in the same territory. The squid does this partly through one biological trick that still puzzles scientists, something about how it uses its body to vanish from view, even in near-total darkness. The video exists. Most people have never seen it, and the few seconds it contains have generated years of scientific argument. In 2019, a team of researchers from NOAA, the American Ocean and Atmosphere Agency, was operating a remotely piloted underwater vehicle in the Gulf of Mexico at a depth of around 3,000 feet. The vehicle carried a specially designed camera system using far-red light, a wavelength invisible to most marine animals, allowing observation without disturbing behavior. The team was documenting deep-sea fauna in an area of unusually high biological activity. The vehicle's camera picked up a large shape approaching from the edge of the light field. The team initially thought it was a large fish. As the shape moved into clearer range, the recording captured something that caused immediate excitement on the surface ship: a giant squid, estimated at around 12 feet in body length with full tentacle extension, bringing it considerably longer, moving actively through the water column at depth. The squid was in frame for roughly 3 minutes before it descended out of range. During that time, it displayed active swimming behavior, jet propulsion bursts, and what appeared to be exploratory movements of its arms. At one point, it extended both long tentacles toward the camera vehicle, in what researchers later described as an investigation or possible predatory approach. Here is the contested detail. At the edge of the camera frame, during the final 30 seconds of footage before the squid descended, a second large shape appears briefly. It is indistinct. It moves slowly. Researchers who examined the footage carefully noted the shape's outline was consistent with a large deep-water shark, possibly in the sleeper shark size range. The squid changed behaviour in the seconds this shape appeared. Its colour pattern shifted, and it rotated its body to orient the rear mantle toward the approaching shape, a posture consistent with a jet preparation stance. The arms pulled in slightly, reducing drag. Then both animals left the frame. The argument among researchers centres on what the second shape actually was. The resolution at that distance and in that light is insufficient for positive identification. Some scientists are confident the shape is a shark. Others argue it could be a large fish or even a piece of debris. The team that made the footage published their analysis without claiming definitive shark identification. What makes this footage significant even with that uncertainty is what happened to the squid's behaviour. The change in chromatophore patterning, the body rotation, the tentacle retraction, all happened in response to something the squid perceived as a threat. Whether that something was a sleeper shark or another animal, the squid's behavioural response looked exactly like what researchers would predict from a squid detecting a large approaching predator. The footage is the closest thing to direct evidence of the interaction that exists, and its ambiguity is a precise reflection of how little humans have managed to observe in the midnight zone despite decades of effort. Something stranger than the question of what was in that video is the question of why the squid was in the Gulf of Mexico at all, given that this region is far outside typical giant squid range. That geographical mystery, still unresolved, opened a new and troubling line of inquiry about whether these animals are shifting their range, and why. A jet engine works by pulling air in from the front, compressing it, and expelling it from the back at high speed. The force of the expulsion pushes the engine and everything attached to it forward. The giant squid's mantle operates on the same principle, replacing air with water. The mantle is the main tube-shaped body of the squid. It is muscular, flexible, and completely sealed except for a narrow opening at one end. To charge for a jet, the squid relaxes the mantle muscles and water floods in through the opening, filling the internal cavity. Then the muscles contract hard and fast, sealing the opening with a one-way valve of tissue while simultaneously compressing the water-filled cavity. The compressed water has nowhere to go except out through a narrow nozzle called the siphon, a tube the squid can aim in almost any direction. The water shoots out, the squid shoots the other way. The mechanics allow the squid to redirect the siphon and control the direction of escape precisely. Point the siphon forward and the squid jets backward. Angle it sideways and the squid curves. The siphon's flexibility means the squid can change escape direction mid-burst without decelerating first. Predators tracking the squid by its original trajectory suddenly find it somewhere else entirely. Measured burst speeds for large squid species in controlled conditions reach close to 25 miles per hour. For a sustained human sprinter, 25 miles per hour is an extraordinary speed. For an animal the length of a school bus, it is something else, a mass moving at sprint speed that requires enormous force to stop or redirect. The kinetic energy of a fully jetted 45-foot squid is substantial. The timing of the burst is what makes it so effective against the sleeper shark specifically. The shark commits to its bite strike in a fraction of a second. Once committed, redirecting the attack requires decelerating, reorienting, and re-engaging, a sequence that takes time the squid uses to build distance. A squid that detects the shark's electrical field at 6 feet and initiates a jet burst has approximately 1 second before the shark's bite would connect. At 25 miles per hour, that 1 second moves the squid roughly 37 feet. The shark's strike connects with water. The catch is that the jet costs enormous energy. The mantle muscles are among the most metabolically demanding tissues in the squid's body. A full burst depletes oxygen reserves rapidly. A squid that jets repeatedly in a short period risks oxygen debt. the underwater equivalent of running to exhaustion. After 3 or 4 full-power jets, the squid's response speed drops significantly. The sleeper shark's extreme patience in the approach may partly be a strategy that exploits this limitation. A shark that forces 2 or 3 escape jets before committing to its actual strike finds a target that is physiologically depleted. Whether this constitutes strategic thinking in any conscious sense, science cannot say. But the behavioural evidence is consistent with exactly that pattern. Old sharks with multiple sets of squid scars on their bodies survived encounters that included failed escape attempts by the squid. The squid has one more defence the shark must get through before any of this matters. It operates before the jet and before the ink, and the shark has no counter to it. Every few years, a giant squid washes up on a beach somewhere in the world. New Zealand, Norway, California, Tasmania. The carcass arrives at the shoreline in varying states of decomposition, sometimes relatively fresh, sometimes badly degraded. Beachgoers photograph it. Scientists rush to collect samples before the tide and the scavengers take what's left. The question of why these animals strand has never been fully resolved. Giant squids live in the open ocean at depth. They have no reason to approach coastlines. Their food sources, their pressure comfort zone, and their temperature preferences all exist in deep open water. The distance from their normal habitat to a beach is enormous in every meaningful biological sense. An animal found on a shoreline has travelled far from where it belongs, and the journey almost certainly happened after death. The current carrying the body. Scientists examining stranded giant squids look for cause of death. The results vary. Some carcasses show evidence of fishing net damage, entanglement wounds on the arms or mantle. Some show nothing definitive because decomposition has obscured the original injury pattern, and some carry injuries consistent with predator encounters. Sucker ring scars have been documented on stranded giant squids, and in some cases the scars show fresh hemorrhaging around their edges, indicating they occurred shortly before or around the time of death. A squid that died during or immediately after a battle with a large predator could drift to a coastline over days or weeks, carried by surface currents after the body ascended from depth as decomposition gases built up inside the tissue. The connection between deep-sea predator encounters and strandings is plausible but unproven. Scientists are cautious about making it a primary explanation because strandings occur for multiple reasons, and the sample size of well-examined carcasses with clear cause of death evidence is small. One observation that researchers find difficult to dismiss is the geographic correlation. Strandings in the North Pacific, particularly along the coasts of Alaska, British Columbia and Northern California, occur in the same regions where sleeper shark populations are dense and where deep-sea trawl surveys show high squid abundance. If strandings were random events unconnected to predator activity, you would expect them distributed more widely along coastlines. The clustering in predator-rich zones at least raises the question. A separate line of evidence comes from internal examination of stranded squids with reasonably preserved tissue. In several specimens, researchers found evidence of what appeared to be rapid pressure change damage, internal bleeding patterns consistent with a fast ascent from depth. A squid injured badly enough during a deep encounter that its buoyancy control fails would ascend uncontrollably. The pressure change on the way up causes additional damage. The squid reaches the surface already dying or dead, and the current takes the body. This sequence, deep battle, injury, uncontrolled ascent, surface drift, stranding, is consistent with all the physical evidence in those specimens. Consistent, though, does not mean proven. The strandings are the most visible evidence of a conflict that happens where humans cannot see it. Each body on the beach is a question mark, and the answer, when it eventually comes, probably involves something deeper than just one predator and one prey animal. It involves the entire structure of the deep ocean shifting in ways that change where these animals meet. Commercial fishing fleets targeting deep water species in the North Pacific routinely bring up animals they were not trying to catch. This bycatch, the unintended harvest that comes up tangled in nets or hooked on lines set for other species, has been both an ecological concern and an unexpected scientific window into what lives at depth. The bycatch record from longline fishing operations targeting Greenland halibut, black cod, and other deep-water fish species in the Bering Sea and Gulf of Alaska contains, buried in decades of logbooks and sample freezers, some of the clearest physical evidence of squid-shark conflict outside of direct dissection. Partially consumed giant squid arms have been recovered from deep-water fishing gear at regular intervals since commercial fishing reached these depths in the mid-20th century. The consumption patterns on these arms tell a story. Bite marks with the curved, wide profile of a large shark jaw appear on some specimens. More significant are the specimens where the arm was not bitten off cleanly but torn, suggesting the squid's arm was separated during a struggle where the squid was moving away from the bite. A clean bite removes tissue in one motion. A torn wound happens when one animal is pulling against the force that is cutting it. The torn specimens indicate active resistance at the moment of injury. The squid's arm was attached to a living fighting squid when it came away. Several fishing vessel crews operating in sleeper shark territory described hauling up sleeper sharks on their long lines that were simultaneously entangled with giant squid remnants. In some cases, the squid tissue was fresh enough to still carry coloration. The crew of one vessel, documented in a Fisheries Observer report from the Gulf of Alaska, described pulling up a large sleeper shark that had a significant portion of giant squid mantle tissue lodged in and around its jaw, with multiple squid sucker rings still embedded in the shark's gum tissue. This type of evidence, recovered incidentally rather than through targeted scientific sampling, adds a dimension to the picture that laboratory studies cannot provide. Fisheries observers have collected these specimens for decades, often without recognizing their scientific value, and the backlog of preserved and logged material in fisheries archives represents an understudied resource for researchers studying deep-sea predator behaviour. One research team that specifically requested access to preserved bycatch samples from a single fishing company's cold storage in Dutch Harbour, Alaska found over 30 separate giant squid tissue samples collected across 12 years that had never been formally analysed. 7 of those samples showed injury patterns consistent with shark bite or shark grip contact. Years of evidence, sitting in a freezer, waiting for someone to ask the right question. The geographic data embedded in these bycatch records also maps, imperfectly but usefully, the areas of highest interaction. Concentrated bycatch evidence from specific fishing grounds aligns with the areas where oceanographic surveys show the deep scattering layer densest, the same areas where sleeper shark populations peak, and the same areas where squid strandings along nearby coastlines are most common. Everything points to the same zones. The bycatch record fills in the geographic picture where direct observation fails, and within those zones, deeper than the fishing gear typically reaches, something even larger than the giant squid hunts the same waters. An animal so poorly understood that scientists still argue about basic facts of its biology. The giant squid is enormous. The colossal squid makes the giant squid look manageable. These are 2 separate species. The giant squid, found across multiple ocean basins, grows to around 45 feet in total length with arms extended. The colossal squid, found primarily in the deep waters surrounding Antarctica, grows to a shorter arm-extended length, but carries a mantle that is dramatically heavier. A colossal squid specimen caught by New Zealand fishermen in 2007 weighed around 1,100 pounds, approximately the weight of a full-grown dairy cow. The giant squid reaches around 300 to 400 pounds at maximum size. The colossal squid is the heaviest invertebrate on Earth. It lives at depths of over 6,000 feet, possibly considerably deeper. Its mantle alone can reach about 9 feet in length, and its eyes, already the largest of any animal in the giant squid, are even larger in the colossal squid. One measured eye from a preserved specimen reached 11 inches in diameter. That is wider than a standard bowling ball. The colossal squid also carries a weapon the giant squid lacks. On the middle section of its longest tentacles, where the giant squid has simple sucker rings, the colossal squid has rotating hooks, These are not fixed structures. Each hook can swivel freely on its base, meaning when the squid's tentacle wraps around prey, the hooks rotate to maximize their grip and bite regardless of the angle of contact. The hook tips are curved and sharp. Scientists examining preserved specimens find they can cut human skin with light pressure. The hooks are angled to resist backward pull. The harder a predator tries to pull a colossal squid's arm away, the deeper the hooks rotate inward. They are specifically designed to make escape for the prey, or escape for the squid, as difficult as possible. Rotating hooks versus sucker rings, 1,100 pounds versus 300. An animal that large, arm that specifically, fighting a sleeper shark, produces an encounter that no scientist has directly observed and few have modelled in detail. Sperm whale stomach contents from Antarctic waters contain colossal squid beaks, confirming sperm whales hunt them. Whether sleeper shark relatives in Antarctic waters, specifically the southern sleeper shark, encounter colossal squids with the same regularity as Pacific sleeper sharks encounter giant squids is unknown. Stomach content studies on Antarctic sleeper sharks are extremely limited. A few available samples contain squid beak material consistent with large squid species, but sample sizes are too small for strong conclusions. The colossal squid's size and weaponry make it the most formidable prey item in the deep ocean by any measure. An animal that evolved rotating hooks on its tentacles evolved them because something was trying to remove those tentacles through force. The hook design is a counter to being grabbed and pulled. Whatever was grabbing and pulling colossal squid arms hard enough to drive that evolutionary response was large, persistent, and dangerous. Scientists haven't yet confirmed what that was. The answer likely comes from the same direction every other answer in this story has come from: the stomach contents of the animals that share the deep with it. And sharing the deep, it turns out, involves a debate that has run through this entire story without being settled directly: whether the sleeper shark is truly a predator or something else entirely. The question has sat at the centre of sleeper shark research for 30 years, and it remains genuinely unsettled. On one side, the active predation argument, stomach beak evidence, fresh injury marks on stomach linings, sucker ring scars with hemorrhaging on sharks, torn squid specimens from fishing bycatch showing resistance at the moment of injury. All of it points towards sleeper sharks actively catching and killing living giant squids. On the other side, the opportunistic scavenging argument. Sleeper sharks are extraordinarily slow. Their metabolism is so low they barely need to eat. A shark that stumbled across a recently dead giant squid on the seafloor would consume it completely, beaks and all. Some squid die naturally. Some are injured by other predators and descend to the seafloor before expiring. A sleeper shark in the right place at the right time could accumulate a significant beak collection without ever engaging a healthy living squid. The scavenging argument cannot be dismissed easily. Sleeper sharks are confirmed scavengers. They gather around whale carcasses on the seafloor in significant numbers and feed for extended periods. Their low energy requirement means they can survive well on intermittent scavenge meals. Scavenging is well within their behavioural profile. The active predation argument gains force from two specific types of evidence that the scavenger model cannot explain cleanly. First, the stomach lining injuries. A dead squid's beak causes damage too as it sits in the stomach during digestion, but the hemorrhaging around fresh injury marks in the stomach walls of sharks examined shortly after a squid meal suggests the beak was already inside the shark before the squid died, meaning the squid was swallowed alive. Second, the behavioural data from accelerometer tags. The movement profiles of sleeper sharks near deep scattering layer zones show directed approach patterns followed by brief acceleration spikes. This is hunting behaviour, not drifting across a seafloor looking for dead animals. A third piece of evidence makes the active predation case harder to dismiss. Squid tissue recovered from sleeper shark stomachs in good condition, before significant digestion, carried a chemical signature associated with fresh muscle activity, specifically lactic acid buildup in the muscle fibres. Lactic acid accumulates in muscles under exertion. A squid that died calmly on the seafloor and was then scavenged would not show elevated lactic acid. A squid that fought hard until the moment of death would. The chemical evidence points at struggle. Scientists who have reviewed the combined evidence generally lean toward the conclusion that sleeper sharks do both. They scavenge when the opportunity presents itself, which is energetically efficient. They also actively hunt, selecting prey they can approach using their electrical sensing and stealth method, including giant squids when the depth and timing align. A predator that scavenges and actively hunts depending on conditions is harder to study than one that does only one thing. Its behaviour varies by context, making predictions from any single type of evidence unreliable. What this debate reveals most clearly is how little direct observation of sleeper shark behaviour exists. Almost everything researchers know comes from inference, from stomach contents and scar analysis and tag data and bycatch. The animal itself, going about its daily existence in the midnight zone, remains largely unseen. That invisibility makes one aspect of the squid-shark conflict genuinely measurable and surprisingly informative: the chemical signals both animals release into the water during stress. An ocean at 3,000 feet deep has no wind, no waves, no surface current reaching it from above. The water moves slowly in deep circulation patterns that shift over decades, not hours. In the midnight zone, a chemical released into the water spreads outward slowly, dissipating over hours or days rather than seconds. This makes the deep ocean a chemical record keeper. When a giant squid is attacked, its body responds immediately with a stress chemistry cascade. Adrenaline-equivalent compounds flood its tissue. The ink gland activates, pushing chemical compounds into the surrounding water. Damaged tissue, if the shark makes contact, releases blood proteins and cellular fluids. All of these chemicals disperse into the surrounding water column and remain detectable at low concentrations for hours after the event that produced them. Other animals detect these chemicals. In the ocean, dissolved biochemicals carry information across distance the way scent carries information on land. A shark's chemoreception system, capable of detecting blood at 1 part per million, can pick up the chemical trace of a squid fight from distances of hundreds of feet if the current carries it in the right direction. Researchers studying deep-sea predator aggregation, particularly around whale fall sites where a dead whale releases enormous quantities of biological chemicals into the water, documented that sleeper sharks appear at these sites faster than random movement would predict. They are tracking chemical gradients through the water, navigating by dissolved scent the way a bloodhound follows a trail, tagging data from sleeper sharks near a documented whale fall in the Bering Sea, showed multiple individuals making directional course changes within hours of the whale's death, all converging from different starting points toward the same chemical source, 1 mile per hour and still capable of precision navigation across miles of open ocean. If this same chemical navigation applies to fresh squid distress signals, a squid fight in the midnight zone becomes a broadcast. The injured squid releases chemicals, the chemicals spread. Other sleeper sharks in the region, potentially miles away, begin moving toward the source, not at speed, because these animals move at 1 mile per hour regardless of motivation, but directionally, following the gradient. The initial fight between one shark and one squid may attract additional sharks over the following hours. By the time those additional sharks arrive, the first encounter has ended. They find chemical residue, possibly ink compounds, possibly squid blood, possibly a remnant of the squid itself on the seafloor if the squid died and sank. Giant squids release their own chemical signals during stress that potentially communicate alarm to other squids in the area. Cephalopod alarm pheromones, documented in shallow water species, trigger escape responses in nearby individuals. If deep-sea giant squids share this communication chemistry, a single fight generates a squid dispersal event across a zone of water hundreds of feet wide, as nearby squids respond to alarm chemicals and jet away. One fight, one chemical broadcast, 2 dispersal responses going in opposite directions. Squids moving away from the fight zone, sharks moving toward it. The midnight zone is not as silent as it looks. Even in total darkness, even at 3,000 feet, every significant event propagates outward through chemistry and physics, touching animals spread across a huge volume of water. What remains hidden is what those animals look like when they arrive, because humans have never witnessed one of these battles from start to finish, and the reasons why turn out to be more complicated than simply not having gone deep enough. The technology to reach the midnight zone exists. Research submersibles have been going to 3,000 feet for decades. Remotely operated vehicles can descend past 6,000 feet. The equipment is available. The question is why? With all of that capability, nobody has ever put a camera on a live giant squid and sleeper shark encounter and watched it happen. The answer has three parts. The first is scale. The midnight zone is not a small room. It is a volume of water extending across thousands of miles of ocean, from the surface to the bottom, with the zone of interest sitting between 3,000 and 6,000 feet down. The squids and sharks that interact in this zone are scattered across that enormous volume at very low densities. A research vessel lowering a camera to 3,000 feet is dropping equipment into a space roughly the size of multiple football fields at any given cross-section, with animals spread miles apart. The probability of any camera being in the right place at the right moment is extremely low. The second is behavior disruption. When a submersible or remotely operated vehicle arrives at depth, it does not arrive quietly. The thrusters create pressure waves and sound. Navigation lights illuminate a bubble of ocean that was dark moments before. Both squids and sharks, operating on pressure wave detection and electrical sensing, respond to these disturbances. Squids flee submersible approach in most documented cases. Sharks alter their movement patterns near vehicles. Observing natural behavior around equipment that fundamentally disrupts natural behavior is a contradiction that researchers have not fully resolved. The far-red camera system used in the Gulf of Mexico in 2019, the same footage that captured possible giant squid and shark near encounter, was specifically designed to reduce behavioral disruption by operating in a light wavelength most animals cannot detect. That system is expensive, experimentally complex, and produces footage of limited visual clarity. It is a step in the right direction, but a small one. The third barrier is time. An encounter between a sleeper shark and a giant squid does not happen on a schedule. A research vessel costs tens of thousands of dollars per day to operate. Deploying expensive equipment to a fixed deep-sea location and waiting for a chance event is economically difficult to justify in research funding structures built around specific hypotheses and predictable data collection. Scientists have proposed alternative approaches. Autonomous underwater vehicles which can operate without a surface ship for weeks or months could theoretically be stationed in high-probability zones and left to record continuously. Advances in battery technology and acoustic data transmission are making this more feasible. A research group in the Pacific has proposed deploying networks of these vehicles in the deep scattering layer zones where squid-shark overlap is highest, running for extended periods, with triggering software that begins high-resolution recording when large animal movement is detected. That proposal has not yet been funded at the necessary scale. Until it is, or until some technological breakthrough makes passive deep-sea observation economical, the fight in the dark stays in the dark. The evidence keeps accumulating from the outside: scars, beaks, bycatch, chemical signals, all of it pointing at something that has never been directly witnessed, and some of what it has pointed at on the seafloor after the fact suggests the encounters leave behind more than just biology. A remotely operated vehicle, or ROV, moves slowly along the seafloor at 3,000 feet, its lights illuminating a narrow corridor of seafloor that was dark for years before this visit. The camera records everything. Most of what it finds is familiar: sediment, tube worms, sea cucumbers moving almost imperceptibly, the occasional fish, and then occasionally something else. Researchers reviewing footage from deep-sea ROV surveys in the North Pacific found scattered anomalies that, taken individually, could be explained in multiple ways. Taken together, they tell a consistent story. The first type of anomaly is isolated squid arms on the seafloor, separated from any body, showing no signs of scavenging removal of the kind that would produce a clean break. The separation point on these arms is ragged, with the tissue pulled and torn rather than cut. Tissue that separated during mechanical force while the squid was alive and moving tears differently than tissue that simply decomposed or was cleanly bitten through. Marine biologists familiar with squid tissue structure identified several recovered arm sections as consistent with force separation during a struggle. The second type is ink concentration. Squid ink in the water column dissipates relatively quickly, spreading and diluting as currents move it. On the sea floor, where water movement is minimal, ink can settle and concentrate in depressions in the sediment. ROV cameras in the North Pacific have documented dark staining in seafloor depressions that, when sampled, contained melanin at concentrations consistent with large squid ink. These stains appeared in areas with no obvious explanation for ink concentration, other than a squid releasing its ink cloud directly above near the sea floor. The third type is the most dramatic and the most contested. In two separate ROV survey areas in the Gulf of Alaska, cameras documented what appeared to be large areas of disturbed sediment covering tens of square feet, with scattered biological debris including what researchers identified as squid tissue fragments, and, in one case, a squid beak sitting on the surface of the sediment rather than buried or dispersed. A squid beak on the seafloor surface surrounded by tissue fragments and disturbed sediment in an area of documented sleeper shark activity is consistent with exactly one scenario. A squid was killed and consumed at or near the seafloor, and the indigestible beak was expelled by the shark and settled to the bottom. Sharks expel indigestible material through regurgitation. A sleeper shark that consumed a giant squid and could not pass the beak through digestion would eventually regurgitate it. The beak landing on the seafloor at depth leaves exactly the physical signature described in those ROV surveys. None of this is proof. Each element can be explained individually through other mechanisms. But the specific combination of torn tissue, ink staining, disturbed sediment, and expelled beak material at the same site, in an area of high sleeper shark density, presents a circumstantial case that researchers find difficult to explain without the squid-shark conflict. The seafloor of the Midnight Zone is covered in this kind of evidence, most of it unobserved and unstudied. Every ROV dive that finds these anomalies is looking at aftermath. The event that produced it was over hours or days before the camera arrived. Something is changing about where these events happen, and the reason involves a force that reaches from the surface all the way down to the Midnight Zone. Ocean temperature is rising. That fact is confirmed by decades of measurement from ships, buoys, satellites, and deep sensors distributed across every ocean basin. The warming is concentrated in the upper layers of the ocean, but the effects propagate downward over time, and they are already measurable at depths relevant to giant squid and sleeper shark territory. Giant squids are extremely sensitive to temperature, as covered earlier in this series. Their hemocyanin-based blood loses oxygen-carrying efficiency in warm water. The zones where giant squids can sustain normal function are defined partly by temperature gradients. As surface warming pushes warmer water downward, the upper boundary of the suitable temperature zone for giant squids moves deeper. Squids that previously lived comfortably at 1,000 feet may need to descend further to find water cold enough for their physiology. This downward pressure on squid distribution has been documented through trawl surveys. In the California Current System, which runs along the west coast of North America, researchers tracking squid distribution over several decades found a measurable deepening of the zone where giant squid are most commonly caught. The deepening correlates with the warming of intermediate water layers in the same region. At the same time, the deep scattering layer, which both squids and sharks follow, is showing signs of disruption. The layer's composition depends on the availability of small organisms at different depths. As temperature gradients shift, the organisms that form the layer respond, and the layer's density and vertical range change with them. Some researchers have documented a thinning of the layer at its traditional depth range and a redistribution of biomass to different depth bands. If the layer thins or shifts, the concentration effect that makes it valuable as a hunting zone changes. Squids following a thinner, more dispersed layer cover more territory per unit of time searching for prey. Sharks following the same layer's lower boundary find prey less concentrated and more spread out. How these changes affect conflict frequency is genuinely unknown. There are plausible arguments in both directions. More dispersed squid distribution could mean fewer encounters with sleeper sharks, simply because both animals are more spread out in a larger volume of water. Alternatively, squids pushed to deeper zones may enter areas of higher sleeper shark density, increasing encounter frequency. The warming effect on sleeper sharks themselves adds another variable. Sleeper sharks are cold water animals. Their physiology is calibrated to near freezing temperatures. As the cold water zones they inhabit face incremental warming at their upper boundary, the sharks may compress toward deeper, colder water. If squids are simultaneously being pushed deeper by warming from above, both animals may concentrate into a narrower, colder zone at depth, increasing encounter rates. Two species being squeezed from opposite ends into the same tightening band of survivable water, meeting more often in a smaller space. No long-term study has yet run long enough to detect a trend in squid-shark interaction, frequency correlated with climate variables. The evidence is circumstantial and the mechanisms are complex. But the deep ocean is changing, measurably, and the animals that have been locked in this conflict for millions of years are responding to a pressure neither of them has experienced before in their evolutionary history. What those two animals together reveal about life on this planet is something that goes far beyond the fights themselves. Two animals that almost nobody has ever seen, fighting battles that no camera has fully captured, in a place no human can visit without armoured equipment, have turned out to be one of the most scientifically revealing relationships in the ocean. The giant squid and the sleeper shark did not become important because scientists decided to study them. They became important because the evidence kept appearing in places scientists were already looking, in whale stomachs, on shark skin, in fishing nets, on beaches, in archived bycatch records, and demanded an explanation. Following that evidence required crossing the boundary between what is comfortably observable and what is not. Every significant discovery in this story happened because someone looked at indirect evidence and took it seriously enough to trace it back to its source. The beak in the stomach, the scar on the skin, the tear pattern on a recovered arm, the stain in the sediment. Direct observation is the gold standard of biology. You watch the animal, you record the behaviour, you draw conclusions. But direct observation has a physical limit. Below a certain depth, at a certain cost, in a certain darkness, direct observation becomes impossible for practical purposes, and below that line, life continues at full intensity, completely indifferent to whether anything is watching. The giant squid and sleeper shark relationship shows that the invisible parts of the natural world are fully as complex, as violent, as ecologically important, and as scientifically rich as anything humans have studied in accessible environments. The Midnight Zone is not an empty basement beneath the productive ocean. It is a complete ecosystem, running on its own logic, shaped by millions of years of pressure, darkness, and the relentless arms race between organisms that have to eat to survive. What we know about this ecosystem comes mostly from scraps: a beak that survived digestion, a scar that outlasted the wound, a piece of arm that rose from the deep in a net, fragments of a story whose full text is written in total darkness, 3 miles below the surface, in a language made of electricity and chemistry and force. The story has stakes beyond the animals themselves. Giant squids, as keystone prey, connect the Midnight Zone to the surface ocean through every whale that eats them and breathes nutrients back up. Sleeper sharks, as long-lived apex predators, structure the distribution and behavior of prey animals across vast stretches of the deep Pacific and Atlantic. The health of both populations feeds back into the chemistry of the ocean itself. A disrupted squid population means disrupted predator feeding. Changed prey distribution follows. The deep scattering layer responds. Surface productivity shifts. One relationship in the midnight zone is a thread in a web that reaches the surface of the planet. The last confirmed sighting of a live giant squid in its natural habitat was brief, fragmentary, and happened in water so deep and dark that the footage required specialized equipment to capture. The last confirmed record of a sleeper shark behavior was inferred from a tag readout, never directly observed. Two of the most significant animals in the ocean remain almost entirely unknown. That is the most important finding of all. The planet still holds places and creatures and conflicts that science has barely touched. The midnight zone is one of them, and somewhere down there right now in cold water and total darkness, a very old shark is closing the distance on something that has no idea it is being followed. The fight is already happening. We just cannot see it yet.